Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and hello everyone. Alright, we're going to continue our lecture at the slide that we stopped during last video. So now we're going to see dt complex exponential and sinusoids. Right, the first one, we're going to look at dt complex exponential. The equation of dt complex exponential is given by xn equals a exponent j omega naught n plus theta. Now, how can we relate with the example that we seen in our last lecture? Alright, for example, we have this equation. Last time we have discussed this. Alright, xn. For example, we just take one term, right? So we have here actually 5 samples. However, we are going to take one sample only. If let's say we have xn equals 3/2 exponent j pi over 4n. How do you compare this term with this term? In this term, the theta is 0 degrees. And what is A? A is 3/2, and omega naught is actually pi over 4. Okay, so now we know that A is the amplitude, theta is the phase, omega naught is the fundamental angular frequency. So that's all for dt complex exponential. And how are we going to convert it into sinusoid? We can convert this term into sinusoid or vice versa by using Euler's formula. Right, Euler's formula is given by these 3 expressions. The first one we used to convert from exponential term or exponential function into a sinusoidal function or trigonometric function, which is cos and sine. And we have another 2 terms, which are, the first one is cos x. We can convert cos x into exponential by using this expression, half times exponent jx plus exponent minus jx. And likewise, if we have sine x, we want to convert into exponential, we can use this expression, which is 1/2j times exponent jx minus exponent minus jx. So these Euler's formula are very important in this part. We want to use in Fourier analysis, these Euler formulas are very important. Now let's see how can we find fundamental angular frequency. Right, the fundamental angular frequency can be found by using this equation. Omega naught equals 2 pi over n, in which 2 pi is the angular that it takes, or the angle that it takes to complete one cycle of the signal, and n is actually the fundamental period. Or we can say specifically for a dt signal, n is the number of samples where the signal repeats over and over. Right, the unit for omega naught is radian per sample. Alright, this is the most important part of this lecture, which is we want to determine whether a dt signal is whether it is periodic or non-periodic. Okay, non-periodic also called as aperiodic. Okay, sometimes you find the term aperiodic. Bear in mind that aperiodic is similar to non-periodic, so they are the same. So now, how are we going to determine whether a signal is periodic or non-periodic? Right, the signal is periodic when it satisfies the equation xn equals xn plus n. Okay, so now to understand this expression, let's look at one example. Okay, that expression is very useful if we have a plot like this plot. So if we have a plot like this, we can determine whether the signal is periodic or non-periodic by inspecting the pattern of the signal. So generally, what can we see from this signal? We can see that you can say that it is periodic very clearly. Supposedly we have like ... because the signal repeats over and over towards infinity and towards minus infinity as well. So this one we just see about 3 cycles of the signal only. Right, we can say now, if you look at the signal, can we determine what is n, or the fundamental period? What is n? Right, if we start here, if we start the signal here at n minus 3, so 0, 1, 2, 3, 4, 5. So you see the value of 0 repeats after 5 sample. Right? So we can say that this 5 as n. Right, but wait, we only look at one sample. Now, I mean one value. We see that when n is minus 3, so if we plug into the equation, we get x minus 3 equals, we say that n is 5 just now, so x minus 3 plus 5, we got on the right side x 2, right? So we see that x, the value at minus 3, is it equal to the value at 2? So we say that it's equal, the value is both, the value are both zeros. So then we can say that the signal is periodic. Alright, we can further examine by maybe we can look at minus 1, n minus 1. Right, count up to 5. Let's count up to 5. Okay, minus 1, 1, 2, 3, 4, 5, right? So the next 5 samples, we see the value is the same. The value is 1, and the value at minus 1 is also 1. Okay, maybe that verifies the signal is periodic. If we want to further examine, go on, we look at when n 0. At n0, the value is 1. So we count up to 5 again. Right, 1, 2, 3, 4, 5. We see the value at 0 is 1, and the value at 5 is also 1. So we say that the first signal, this plot is periodic signal. Alright, what about the second example? Look at the second example. So now we can see the pattern as well. It's about, we have about three cycles as well. So this actually, we have ... here and ... there, up to infinity, up to minus infinity. So if you look at the pattern, we can say that the pattern repeats after, for example, if you have here minus 3, so it zeros again at n equals 2. So if we anticipate that this is actually the smallest number of samples that the pattern repeats, so we say that from minus 3, 1, 2, 3, 4, 5. So n is 5 as well. N is 5. We can further examine. At n minus 2, So next 5 samples are the values, is the value is still the same, right? So let's say -2, we take 5 samples further. Okay, 5 samples further. Okay, from -2, 1, 2, 3, 4, 5. We say that -2, the value is 0.5, and at 3 also the value is 0.5. So we say that the signal is periodic. Same if we examine at -1, right? At 4 the value is the same, so on and so forth. So this determines that the plot in example 2 is a periodic DT signal. Alright, what about non-periodic DT signal? So it is obvious in this plot that we can see the signal doesn't repeat. The signal doesn't repeat. Or if it repeats, maybe it takes like approaching infinity, only the signal appears again. So we can say this time obviously, because if you look at the pattern, there is no other values on the right side, there is no other values on the left side. We say that the signal is non-periodic or aperiodic. Same with the example 4. We can see there are only 3 samples in the signal. It is not repetitive. There is no repetition on the both sides, to the positive infinity and to the negative infinity. So we say that this signal is non-periodic.